Okay, 7.5, I put a yellow line in there for DDAM calculation, which means a dynamic design analysis method, which is one of the methods Navy has been used for a long time. That DDAM I mentioned to you, and we go through all the behind the story. Then in chapter 8, I'm going to give you like a procedure cookbook, okay? So input, remember this, the input-based excitation is applied to one principal direction at the time to compute the response of the structure. This is really the method, and there is a procedure. But for example, you have a ship here, and I can put this as 3 direction. So this direction is vertical. This is the principal direction of the motion by underwater explosion, vertical. Okay, and this is a fore and aft direction, and this is authorship direction. Authorship direction. 3 direction. So DDAM approach is the procedure again here. You apply the excitation, for example, in first vertical direction. First, the explosion occurs right under. So first, well, doesn't have to say first, but 3 direction, not simultaneously, 1 direction at a time you apply the excitation. First, in vertical direction. Second, the fore and, well, like authorship direction. Third is the fore and aft direction. Because all that DDAM in trim report, NRL 1396, this report provide all the coefficient need to do the calculation. So one of the requirement is, as I said in the first line, the input-based excitation is applied to one principal direction at the time to compute the response. This is 3 principal direction, but apply the excitation 1 direction at a time. So this is, they try to make it more conservative, but as I said, it's not really true to say it is conservative, but all the methodology, this is the requirement, it worked really well. That's the reason this approach has been accepted for a long time, used for a long time. So he said each lumped mass has 6 degrees of freedom system, 3 translational and 3 rotational, 3 translational and 3 rotational in XYZ principal direction. So if I put this as X, Y, Z, okay, I'm gonna just say, okay, this is, let's say, X1, then it's gonna be X2, it's gonna be X3, okay? By the right hand rule. Or you can set this guy, this direction as X1, it's all up to you, right? Then X2 and X3, by the right hand rule. So that's up to you, but that's what I just put that in. So here we assume the foundation motion Z1 is in x1 direction for the discussion purpose. For discussion purpose, I'm going to just use the Z1 as x1 direction. For the convenience, I'm going to put this guy as x1. If this is x1 by the right hand rule, what would be it? Then for the convenience, I'm going to change this guy as, which one would be a good idea? If this is x1, I'm going to put this guy as x2. Is it true? Then I'm going to say, you set this direction, 3 direction. I'm going to say, for the convenience for the right hand rule, I'm going to say this guy is x3. How's that by the right hand rule? Make sense to you? So I'm going to say that the Z1 direction, what's a Z1? That's the kickoff direction, for example, here. So that's what I put as x1. So you have to do the x1, next to pick out the x2, next to pick out x3, then apply input excitation one direction at a time. So I'm going to apply to x1. That's what we have been using. Okay, vertical directions. But this is a really major direction of the motion, remember. And authorship direction, this is authorship direction, is not the major direction, but in my experience through the ship shock testing, it has a significant amount of the motion, not as big as the vertical. But fore and after direction is in axial direction is absolute minimum. But shock, DDAM procedure saying consider all 3 directions, not simultaneously together, one direction at a time, then pick out the max. Okay. So we're going to assume right here the foundation motion Z1 is in x1 direction for discussion purposes. So you have an equation of motions, right? Right. Y is x minus z. Then now we introduce not only translational direction, but also rotational motion. So I can write, this is all matrix notation. M is something like a mass matrix at each node. This I is the rotational inertial force, okay? Rotational mass moment of inertia. Rotational offset. So if this is a node, you can think about the simplest model I could say is this mass is not right at the center of the node, is offset. For example, you have girder or stringer, something like this. Then if you consider this as a ship stringer, then it's offset. So for example, this is your ship. Any element whose CG is not here but here, then there is the rotational mass moment of inertia, because it's offset. It's offset. CG could be right down there. Got it? So this M and I. This is a translational. I put the T as translational and double dot. Theta double dot is rotational. This is rotational degrees of freedom, like the angle. So this is angular accelerations, okay? And the KT is related to the translational degrees of freedom. This is coupled between the translational and rotational. K theta, this is rotational stiffness, right? Yeah, it's a theta. Then minus, and this is the same as up here. And then here, Y matrix here, Y is, I split into two partition vector. One is a translational vector, the other one is rotational vector, okay? It's kind of a conceptual like work. Then YT is translational. YT, this is a self-vector. Then I put all the x1 directional relative displacement here, and this is for x2, this is for x3. So y is x minus g, okay? And theta is another sub-vector collecting rotation about the x1 axis for x2, x3. So we assume first the excitation is in what direction? The x1 direction, which we assume that's a vertical direction, one direction at a time. So now one direction at a time. So if I split this guy Z as translational and rotational, rotational is 0. For excitation direction is concerned, excitation direction is in the x1, x2, x3 translational direction. This is this second part is all 0. So in this case here, as you look at Z as x1, x2, x3, and this next 3 sub-vector is theta 1, theta 2, theta 3. Okay, that's all equal to 0 for excitation-wise, right? Then Z can spell out as a Z1, 0, 0, 0, 0, 0. Next, if you are going to say excitation is in x2 direction, this is going to be the Z. You can say same thing if you want Z1, Z. Excitation is in that direction, all the others are 0. If excitation is x3 direction, this is going to be a non-zero, but all others are 0. Okay. Then you can rewrite that equation, this equation set into this. This small m is same as capital M, okay? Sorry on that. This is, I use a capital M here, capital K. So it's a small m, capital M is all same. I should modify, but it's the same, okay? Minus m alpha Z1. The difference is right here. Alpha Z1 double dot, because Z is right here. I want to split, okay, into sub-vector term. So introduce alpha. Alpha is concerned in x1 direction is 1, all others are 0. Then bring the modal participation vector. We have done that the Wednesday. And this is expanded form. But over here, this 1 means x1 direction. So in x1 directional component, you could have x2, you could have x3. So here assume the excitation is in x1 direction, so I put the 1. Okay? And what's the mj? This is a modal mass. It's a jth modal mass. It's very important to determine how many modes you are going to include for analysis. You have to get the modal mass. First modal mass, second modal mass, third modal mass. Keep adding up to what? Up to 80%, met the 80% criteria. Okay? Then maximum dynamic force, this matrix is what you have to, as I indicated, very important. Then force, this is a force. The force 1, force 2, up to force m. Why this is m? M is less than or equal to n. Because this is a total number of degree of freedom. So this m should be less than n. Why? Because you don't include all the mode. You just include the mode which can take up to 80%. So here, this is, the rho is the degree of freedom. And of course, the column is what? Mode. So every column, which means every mode, and this has nothing to do with the time. This is not the time domain variable. It's all the static modal force vector. Then you apply this force in your system, structure system. Okay, so that's what this means. Mode, first mode, second mode. Then you have m different modal response based on this. Then get the response in every mode, static response. Then what do? After you got the static response, apply NRL sum. And Willis, you may have a chance to use this for Singapore, the naval ship application. If you build like a high-speed craft maybe. High-speed craft is not just a few hundred pounds, no. Like over 1,000 pounds. That's still high-speed craft. Okay, that's what the U.S. Navy is building. Trimaran, 3 hull system. So middle is a main hull, and you have a 2 side hull. So that's trimaran. That's over 1,000 pounds. Apply this DDAM rule to get to have a shock qualification for equipment. And as you see there, the Fij is that component. You need that. And the omega j and the Vj is what? Aj, right? omega times velocity is acceleration right here. Omega j, Vj is Aj. There is a criteria in DDEM to pick whichever smaller you have to select. This is a rule, procedures. But technically, Vj times omega j is Aj. Okay? And you know the Mi, you know phi j. This is omega j modal frequency, jth mode participation factor. This is a jth, the modal vector, which is a function of omega j. So this is all, the Fij is the function of the omega j, which is dependent mode. This j is a mode, and I is a degree of freedom. So that's what you will always end up to construct this. Number of rows is the number of degree of freedom. So usually if you have a 10,000 the node or 10,000 element, roughly node times 6. That's the total number of degrees of freedom, and this is columns a number of the mode. Okay. Okay, so some references are here. So all this, this is 4 and 5 are all in chapter 8, chapter 9 in that area. So you don't really need to look back. This is published in 1963 and 1965, vice versa. Okay, so chapter 7 is complete, and the next section, next chapter wise procedure to put all the lectures together. And first section is to show DDEM procedure based on our understanding. And this, when you say DDEM, then it connects to the mode, the modal analysis. Then get the natural frequencies and mode shape. That means, well, I'm looking for natural frequencies and mode shape, mode. That means you are dealing with the elastic system. You are dealing with a linear elastic, because DDEM contains on principles of superposition for the result, which means what? Adding the modal result together. That's valid for linear elastic analysis. So here, assumption is linear elastic. So I want you to read all this. Then back to step by step, back to this equation. So my double dot plus ky is equal to minus m alpha. It's come into picture. And z1 double dot, that's what you saw many times. Then same thing. You have to compute now Fij for I is equal to 1 to n, and j is equal to 1 to m. M is number of mode to be included in the analysis. And as I said, omega j Vj is Aj. Aj is modal acceleration. Then matrix notation for the same thing. Then this is a modal participation factor. This is for j's. So this is 1 is x1. That's a direction of the motion. here is x1, x2, x3, okay? So then mj you have to compute. Then mj multiply g and multiply g, then you will get the modal weight rather than modal mass, okay? So I said important point in DDEM, input excitation is applied in one principal direction at a time and can cause the response in all directions. Apply the excitation in x1 direction, that doesn't mean that the response gonna only occur in x1 direction. No, even if you apply the shock in the vertical direction, the members, okay, structure members in the ship can have response in all direction, x1, x2, x3 direction. So this is what you need to compute. Basic quantity, basic equation, you have to compute Fij, then you have to compute the Pj and Mj. Mj multiply G gonna be modal weight. That's what you need. That's about all. The reason I really put different section is after I wrote this up, then I feel, well, let's do again and again to just doubly let you know the step by step to compute the DDEM. That's why it's 8.3, same thing over and over again, same thing. But let's look at the section 8.2. This is NRL 1396, the report. Okay, this is unclassified or declassified in 1985. After 25 years, they declassified it. I reconfirmed, and that's why I put these things in right here. Equipment response type, elastic response, elastoplastic response. Two different responses were considered for the shipboard equipment. One is alignment sensitive equipment, like a propulsion shaft. If it's a bend, it's a big problem. But like a DDG class ships or frigate, one time I visit with the naval students to the shipyard, and we found out that they have a long propulsor shaft, then it's like a serpentine, like a snake. As I look from the one end to the other, it's not straight. I have to use, maybe I forgot the period to inspect. It's serpentine. It wiggles like a snake. Wow, that rotate? Yes. Then they have to bring back to dry dock to really straighten up. That's an art, to straighten up the shaft. And of course the shaft is connected by sleeve. So it was long by using the torch that all the peoples has a skill to running around and straighten up. That's all the method. A new method they claim is better, but all that engineer, they feel that's better. So I don't know. But regardless, they have to. So such a shaft is alignment sensitive. That alignment sensitive equipment has to put that in the elastic. If it's elastoplastic, what does it mean, elastoplastic? Some ice cream machine, you know, if it has some damage, they could miss to have ice cream in the dinner time or lunch time. But that's okay. So elastoplastic response, some equipments allow for some damage. Okay? That's called elastoplastic response are allowed for some equipment. But for naval officer, as Willie is here, the ice cream machine, very important shipboard equipments. They have to have ice cream all the time. Well, it's nice to have. So, but it allows some deformation. That's okay. Lots of equipments, even if it has some damage in there, and as long as it works, that's okay. So you categorize elastic and elastoplastic, the responses. Equipment mount. Some equipment mount right on the hull, and some equipment you mount on the deck. Some equipments you mount shell plating, which is right on the shell. Okay, so you have to consider: is it the equipments below the water or above the water? So two different types you have to consider. Hull-mounted equipments and foundation system mounted directly to basic hull structure, like a structure bulkhead below the water line and shell plating above the water lines and so on. But you don't have to much worry, because when you build a naval ship, you have a ship manual, or you can call the ship's, rather than saying manual, ship spec. So for that ship, then it spells out everything. Consider this as elastic, consider this as elastoplastic. So that ship spec, you must have it. Then you have to follow the guidelines. Any ship you build has to have a ship spec, or ship manual they call. So 3 mount: hull mount, deck mount, shell plating mount. Sometimes it's confusing. So the chapter I included, chapter 11, or one section in 8 point something has also same thing. But take a look at chapter 11. I pulled this out from chapter 11 to show you how to designate hull mount, deck mount, shell plating mount. And the deck mount is like a 1/. This is a deck mounted equipment, hull mounted equipment, and shell plating mounted equipment there. Let's examine this. Like shell plating mounted, as you look at shell plating mounted, can you identify? Oh, this is like shell plating mounted. This is really a hull, and when this is above the water line, then you can call the shell plating. This is a hull. So that's about the only case here. But this crossbar is like this, hull plating mounted. If this is like below the water, then this is it belongs to hull plating mounted. And this guy, that guy is at the hull plating mounted. It's confusing. Even in the shipyard, engineer, he called me one time. How can you say this is this guy, that guy, that guy. How can you say that that guy is a hull plating mounted? This is a hull. And now this is really side wall mounted or shell plating mounted, but this is connected to this, but this is a compressive element. It goes and touch down to where? Hull. Then this is classified, this as classified as hull mounted. It's all how the stress wave gonna go and stop. Go stop where? Hull. Where it goes stop? Hull. Okay? And the deck mounted, this is a deck mounted weir, but it's connected to this wall. Then it stops where? On the deck. So that's a deck mounted. Or anything directly mounted on the deck is a deck mounted. Okay, so that you shouldn't confuse it. This is what? This is a deck mounted because this is all the way down to the deck, stops. This is a deck mounted, clearly deck mounted. This is a hull mounted. It's sometimes not easy, but close to that vertical element which goes down to the hull, but close to this wall, vice versa. Got it? Very easy to determine what mounted. And the criteria, shock design criteria. Shock design value, DJ, you need shock design value to pick out the right value from the NRL 1396. This is that's showing in this section. Shock design value. Okay, shock design value is acceleration value. That's what you need. And the minimum value you must use is 6G. You pick out all the values from the NRL 1396. Regardless, minimum G acceleration you must use for shipboard equipment design is 6G. Okay, you are not gonna go below 6G. Minimum is 6G. And as you see here in the spectra chart here, graph, the V is sensitive in the medium type of the frequencies, and for the high frequencies, acceleration is more sensitive. So minimum is 6G. 2316 is 6 times the acceleration, 386 inch per second square, or here's 9.81 meter per second square, okay, in metrics. So here is all US gravitational. So you have to compute. It's a picking criteria. DJ used for response calculation shall be the lesser of the two values in the same units which are computed from the design value Vj and Aj. Vj, Aj we did as a component in the Fij. We're going to review again here. In no event shall DJ be less than 6G. DJ is equal to the lesser of Vj times omega j or Aj times G. So AJ you pick here is number of G's, okay? But I know it's still, some of you may not be comfortable, but as you keep reading, it's gonna get comfortable. Where AJ, VJ are defined in the next section, and this is a modal frequency in radian per second. This is, of course, cycle per second. And G is acceleration, gravity. In this case, is in US gravitational, vice versa. Okay? Then again, Wj is mj times g. So this is a modal weight. You have to compute this. Then divide by 1,000, change it to kips. 1 kip is 1,000 pounds, okay? Because the reason to change to kips is in the table, they are dealing with a kip, so you have to divide by 1,000. Not a big deal. Now this design value formula. This is the key table to design the shipboard equipment. This is the most important. Until 1985, it used to be classified. Now it's unclassified. Wj in the following table is modal weight in kip. That's why we divide by 1,000. First, ship type. Okay? First, ship type is two different kinds of the ship is what we are dealing with. One is ship type. Ship. What? Surface ship. The other one is submarine. You have to identify where that shipboard equipment goes. Surface ship or submarine. So ship type in this case, this table A is for submarine. And next one is mounting location. So mounting, you have to know where that equipment's gonna be mounted. So mounting, you have to decide, well, you should know, mount. So mount is, you have a hull mounted, right? Hull mounted. Next one is what? Deck mounted, right? And the shell plating mounted. So that location you have to identify. Then you have to compute this so-called reference equation, A naught. A is acceleration. If you have answer is 2.5, that means 2.5, then multiply to g to get accelerations, okay? V naught is, in this case, this is inch per second. So this is when the report saying A naught, V naught, we call as a reference quantity, okay? And this is Wj, W. So every mode you have to compute A naught, V naught. Then the next one is a design value. So it's a design, I can say response type. Response type means elastic or elastoplastic. Whether the equipment which is very sensitive to the alignment, then that's elastic. Any equipment which doesn't allow the permanent deformation, then that belongs to elastic. If it allows some damage, okay, some damage is okay, then that's elastoplastic. That you have to decide. Then in this case, we are working on the vertical excitation. So for the vertical excitation, we'll pick the value in this line. If it's elastic, then you have to compute. It said AJ is 1 times A naught, VJ is 1 times V naught. Then this is the value for elastic. And if it's elastoplastic, then you have to pick that. Then you have to compare AJ times G and also omega J, you know omega J times VJ, compare whichever less, you pick that out, that lesser value as a shock design value. Should be clear. Then next you're going to do the authorship. First the vertical, we are doing it. Next is excitation in authorship direction. And third is forward and after directions. You have to examine all 3 directions. So now it's a deck-mounted equipment. Deck-mounted. Then this is a submarine category, is a submarine. Then you go through all this for the deck-mounted equipment. Then you go through A naught, V naught. You go through the look at this table, elastic, elastoplastic. So you just keep moving. If it's a shell-mounted, you have a different set. Okay. Then next, if your ship type is a surface ship, then you have to go through and pick out the right AJ and VJ. Okay. J is from 1 to M. Very systematic. All the similar equipment said. Some said some equipment's elastic plastic is not allowed. No deformation is allowed. Then you have to stay on the elastic response. So now I put again in section F, item F, the selection of shock design value. Using NRL 1396, you have to select the shock design value. How? First, note type of the ship, surface ship or submarine, right? Second, select the type of the mount, hull mount, deck mount, or shell plating mount. Third, compute the modal weight, WJ, you have to call WJ modal weight, okay? Multiplied by, divided by G. Multiply by G to the modal mass to get the modal weight. Then you have to pick out the proper A naught to V naught from the reference equation from 1396. Then you compute the AJ, the VJ, depend on whether this is vertical or authorship or forward and aft for the shock input. Then multiply AJ to G, then VJ by omega J. Then you compare the 2 value. Then pick out the lesser than 2 value, but that 2 value, if lower than the 6G, then you have to pick out the minimum as a 6G. Is it clear? Should be very clear. Then you're going to read more over the weekend and so on.